Today we're going to talk about fluidization. Fluidization involves any set of particles that are put into a fluidized state by a fluid, which can either be liquid or gas. So in the diagram over here on the left, I have a picture of a bed of particles indicated by the black squiggles down here, and they would have some density, rho p. There's some fluid, again a liquid or a gas, with the density of the fluid, rho f, and as it fluidizes the bed has some height to it, given as height h. And so from the information up in the equation in the upper right here, from the density difference between the particles in the fluid, the effects of gravity, the height of the bed, and then the voidage, so E being the voidage of the particles, we should then be able to calculate the pressure drop, delta P, across that fluidized bed. For a more ideal situation, you can look at the diagram over on the right and see the effect of increasing particle velocity on the pressure drop delta P. And so initially, at zero velocity, you have zero pressure drop, and as you increase the velocity, you end up with a linear increase in pressure drop up to a point. That point is called the minimum fluidization velocity, and that would be the point where the particles now are going to become fluidized, and this is where the pressure drop levels off to a constant rate once the particles are now fluidized. You will notice there's a little bump in the diagram here. Typically that would be because the particles have been somewhat compacted and those particles are sticking to each other, and so it takes a little bit more pressure gradient in order to get those particles to separate and fluidize, and then we quickly recover back to our stable, steady state. Once the bed has been fluidized, you can actually end up with two different types of fluidization. You can have a non-bubbling fluidization, where the bed simply is going to expand to some new height as the voidage increases and the bed becomes fluidized, or you can end up with a form of bubbling fluidization, in which case you will get bubbles of the gas, or usually it is the gas, not a liquid, that will show up inside the fluidized bed, and therefore expand the bed even further, but with these large bubbly gas masses in the center. And for certain types of powders, which we'll talk about next, you may begin with a non-bubbling fluidization, and then as you increase the velocity, end up getting a bubbling fluidization. So there are different types of fluidization. I mentioned the bubbling and the non-bubbling, and there are actually two other kinds as well. And they have this classification system called the Geldart classification, which will classify the powders based on the particle diameter and the relative difference between the particle density and the fluid density. And so the first particle type, which is the primary type that we would like to see, is classification A. And so everything in this region here is classification A, which would be particles that are between approximately 0.1 and 1 millimeter, but that size range between these two lines is also dependent on the relative density difference. So it can be particles all the way down to perhaps 10 microns, so we've got 10 microns, 100 microns, all the way up to 1 millimeter. And this is the type of fluidization where it may begin as non-bubbling and then slowly go into bubbling. The next classification of powder is type B, and type B would be up here between these two lines. This tends to be for particles which are a little bit on the larger side than the ones in type A, and these type of particles only give rise to bubbling fluidization. There is no non-bubbling fluidization at this point. The third of the four types is type C powders. Type C powders tend to be down in this lower left-hand region, where the particles tend to be much, much smaller, and particles that are much smaller tend to have a greater surface to volume ratio, therefore they are much more cohesive, and whenever they're cohesive they stick together. And so in the strictest sense, these powders in class C are not actually fluidized. You get large lumps of particles that may move up and crack and then fall back down, but you're not fluidizing individual particles. And then the final type of particle is the even larger particles, which are called type D in the upper right-hand corner. These tend to be particles that are on the order of 10 millimeters in diameter or larger, and these are ones that give rise to what's called a spouting fluidization, where the air will take a quick spouting route through the very center of the particles, and many of the particles will stay on the side. And as they flow into the stream of air, they will then spout back out the top, and it looks kind of like a fountain. One way I like to use to think about these four classifications of powders, A, B, C, and D, is that A is what you want. You want the regular particles that will fluidize and may eventually become bubbling, but everyone wants to get an A in a course, and therefore that is the ideal situation. B is for bubbling, and that's self-explanatory. C is for cohesive, meaning that their particles are sticking together so strongly that they won't fluidize. And then D you can think of as diameter, as a large diameter particle, and these larger diameter particles will form these spouting beds.